Hi, everyone. The next topic is goodness of fit for logistic regression. For linear regression, we have some intuitive measures such as R-square or estimated error size, the sigma hat square. So R-square represents the percentage of variability in data explained by the predictors, and the sigma is the standard size of error for linear regression. But logistic regression, we haven't discussed an intuitive measure. We have the deviance, but when we are given deviance, it's not really sure how to interpret the deviance number itself. So the easiest way to summarize the result of logistic regression is contingency table. So the idea is simple. So we have two categories for actual and predicted. So we have logistic regression, so binary, so actual values are 0 or 1, and also predicted value is also 0 or 1. So as long as we can define the predicted value, our decision, we can see that if the actual is 0, predicted is 0, then we say this is correct, and also 1, 1 correct, but others are incorrect. So if we use this, if we can construct contingency table, we can see the result at a glance. So how to decide predicted value? So typically, we use the threshold at 0.5 because 50% is kind of the midpoint. So if y is equal to, so probability of y is equal to 1 is larger or equal to 50%, that we decide predicted class is 1. Otherwise, 0. So the inclusion of 0.5 is just controversial. So maybe you can exclude the first one and you can include the second one. But that is the rule. Okay, in the previous example, that we can calculate that predicted value. Okay, so we choose the best model. Okay, so by stepwise model, that we choose the best model. Then, okay, so we omit all NAs. Then after that, we make contingency table for predicted value and the actual value. So predicted value is obtained by fitted value of the best model, and we see if these numbers are less than more than or equal to 0.5 or not. So this is the table. So at first, the actual value is either no or yes. And so you can see that most observations have actual value equal to no. And some observations, yes. And the predicted value, mostly no. Because anyway, so the actual value is no with more than 90% probability. So predicted probability of larger than 50% is pretty unusual. That is very high risk volunteers, only 5 people. Okay, but still this table makes some sense. So this and this are correct. You can see that with this group, actually, if we think about the people who are predicted as no, the most people are actually no. And if predicted class is yes, okay, so a little less than 50%, but still the 2 out of 5 volunteers have actually yes. So that ratio is at least much better than this class. 253 over the summation of this 3,135 is much smaller. So in some sense, this table makes some sense. And if you want to further summarize this data, you can calculate the correct rate. So correct rate is correctly diagnosed individuals over total. So total is actually the 3140. So this is total. So this is about maybe 92%, 3%. But actually, this 92% or 3% looks good, but actually it's not that good because the baseline of correct rate is just the, in this case, number of no over total. Because if we diagnose all patients, all volunteers as no, then at least we can achieve this baseline. So this baseline is 2885. So summation of these two numbers over total. So actually this is even better than the correct rate by our decision rule. So if the baseline is around 50%, this contingency table usually makes sense for a reasonable prediction model that we have correct rate much higher than the baseline. But in this case, since the data is skewed, most observations have the actual value no, and only few observations have yes. So this contingency table that doesn't work very good.